Okay, see, actually, the point is, uh, see, if so, totally we have 8 bits. Totally we have 8 bits. If all the 7 bits are one, it is not 128. It is 127. Okay, if all these 7 bits are one, if all these 7 bits are one, it is actually decimal 127. It is actually decimal 127. Okay, so uh, so plus 127 to minus 127, it's not an issue. There is no question. Okay, it can represent. I think you don't have any doubts. If this is zero, if this is zero, then it is actually going from uh, 0 to 127, right? Plus 127. Okay, if it is if it is 1, if it is 1, then it is going from minus 1 to, because 0 already we have represented, so it goes from minus 1 to minus 127. Okay, that is also fine. Okay, how come this 128? So this is what I want you to understand. How this 128 comes. Okay, this 128, how it comes in the sense, actually this is the minus 1 is what? Minus 1 means sign bit is 1, and all these things will be 0 0, everything will be 0, the last bit will alone will be 1. Okay, so extra this 128, from where it comes? So this extra 128, how it comes in the sense, if the most significant bit is 1 and remaining all are 0, and remaining all are 0, okay, so then this is what? This is 128. Okay, this is how we got that extra 128, right? So this is how it ranges from minus 127 to plus 128. Okay, uh, this is the normal case. Okay, but actually IEEE uses only from minus 126 to plus 127. It is not using this minus 127 and this 128 for normal operation. These are used to represent some special values. Okay, right? Actually this minus 127 represents 0. This minus 127 is equivalent to 0 in excess 127 notation. There is some notation called as excess 127 notation. Okay, so this minus 127 will be equivalent to 0 in a particular notation, which is called as excess 127 notation. So excess 127 notation means what? Means whatever the given number, to that you add 127. So to minus 127, if you add 127, then it will become 0, right? So minus 127 plus 127 is actually 0. Okay, similarly, if you this 128 is also in excess 127 notation. So to this, if you add 127, you will get 255. Okay, you will get 255. So actual 0 and 255 are used to represent some special conditions. What are the special condition? 0 is used to represent exact 0, and 255 is used to represent infinity. Okay, so in mathematics, these are the things which we may have to represent, right? Okay, then you may ask, in this range also there is a 0. No, what will happen to that? So that 0 is also actually in, all these are represented in excess 127 notation in IEEE format. Okay, so so the point I'm uh, trying to make you understand is, whatever the number given in this exponential part, it is actually in excess 127 format. Okay, it is not in normal format, it is in excess 127 format. That is, whatever the number is here, it should be added with 127 to get the actual value. Okay, so if it is 0, then you add with 127, that will be actually 127. Okay, right? So then what is 0? Minus 127 is the actual 0, because when you add 127, you will get 0, right? Okay, so these mantissa are actually represented in excess 127 notation. Okay, so this is the minimum value you can have for, sorry, exponential. This is the minimum value you can have for exponential, that is minus 126, and this is the maximum you can have for exponential, that is 127. Okay, so when it will be minus 126, if actually that exponential is 1, minus 1, if actually that exponential is minus 1, okay, then if you add 127, then if you add 127 minus 1 will be minus 126. Okay, and when it will be 127, when it will be uh, 127. So if it is uh, if it is if it is 0, then it will be 127. Okay, right? Okay, so the minimum value that can be represented is minus 126. Okay, and the maximum value that can be represented is 127. Okay, anything less than this will be underflow, and anything more than this will be overflow. Okay, similarly, so this is for 32-bit numbers. Similarly, for 64-bit numbers, this is the range. Actual range is from minus 1023 to 1024, but it takes from minus 1022 to 1023, right? That is it uses the 11-bit, right? Okay, so now let us see how addition will be performed in how addition will be performed in floating point numbers. Okay, so this is a normal addition, so this number should be added with this. Okay, so first you have to check which has the highest exponential. This has the highest exponential. Okay, so you have to match this number's exponential also equivalent to this. Okay, so if you want to match it, then you have to right shift. Okay, you have to right shift. So this, if you bring this 1 here, then it will become 10 to the power 7. Another 0 point if you add, it will become 10 to the power 8. Then another 0.0 you add, it will become 10 to the power 8. Okay, so like that you convert this number from this notation to this notation. Okay, after converting, just add these two numbers. Just add these two numbers, and the exponential will be whatever the common one. That's it. So this is how addition is done. How multiplication is done, in the sense, whatever take the exponential part of both the numbers, add these two, 8 plus 6. Okay, so 8 plus 6 is 14. So keep that as the exponential form, and then just multiply these two numbers as usual. So whatever you get, so that is the output, right? And for division, take this exponential format and just subtract this 8 minus 6. Okay, and just divide these two numbers. Okay, so this is how division is done in floating point, right? So whatever we have discussed, that rule is listed here. So choose the number with the, this is for addition and subtraction. Choose the number with the smaller exponent, shift its mantissa to the right until the exponents or become equal, add or subtract the mantissa, determine the sign of the result, normalize the result if necessary. Normalizing means adjusting the exponent by shifting left or shifting right. Okay, okay, here we are not doing the overflow or underflow. Sometimes if the number is bigger, it may create overflow. If it becomes very small, it may create underflow. And this is for multiplication. Add the exponents for multiplication. Okay, and for division, you have to add the exponents and multiply the mantissa and determine the sign and normalize the result. Okay, sometimes you may have to truncate or round the mantissa, right? And for division, subtract the exponent, add the bias. Okay, add the bias, divide the mantissa and determine the sign of the result and normalize the result, and truncate or round the output. Okay, fine. There is something called as God bits. What is meant by God bits? God bits in the sense, see, sometimes when you normalize, when we are normalizing, we are shifting right or shifting left. Okay, say assume that you are shifting right. When you are shifting right, these bits you may lose. Okay, sometimes if there is a 1 here, then you may miss that 1. Okay, then the precision may be missing. Okay, but if you want to avoid that, then this, whatever the bits you are moving out, that can be stored in a special bit which is called as God bit, So normally we perform normalization to perform addition or subtraction, whatever it may be. Okay, so store these God bits here, so that it won't be lost. Then perform the operation, and then you can move the God bits to the actual number if required. Okay, so that is called as God bits, right? Okay, fine, let us stop here. Yes, thank you.